So for final test, I'm going to go to motor and final test. And then turn off my alignment, remove the power cable from the alignment and hook it up to our run-well drive here. Always attach the shield on the run-well drive. And then, as always, the Linea communicates with the run-well through the Ethernet cable. So this IP address should match what's flashing on the front of the drive. And as long as it is, we can go ahead and click connect. And once we are connected to the drive, we just got to program the drive with some basic information, almost always found on the nameplate of the motor. So in this case, my current is 9.3 amps and my torque rating is 4.9. And the rated maximum speed is 3,000 RPMs. And this motor has no brake. If you're not familiar with the final test, the analytics time is defaulted based on the feedback type that we're working with. These are the test minutes that are going to be used during the test. So in this case, it's only 2 minutes because there's only one channel to analyze. And the runtime is the free runtime that, to be clear, does not use test minutes. That's how long you're going to run the motor to get the motor hot. So you can run analytics while the encoder is cool or room temperature, and also when it is hot and under heat stress. So normally for a motor this size, I would run it for probably about 30 minutes minimum. For this example, I'm just going to leave the runtime at 1 minute. And our test speed is going to be, we'll run it at 1,000 and leave the acceleration and deceleration as is. And then once all that's filled out, we'll just hit configure drive. By default, the first thing we always do when working with the run well is to clear faults to make sure the drive is not in a faulted state. And then once we hit enable access, we will be putting current into the stator windings. So at this point, the shaft may jump and the motor may jump. So please make sure that you have the motor secure. All right, and then we can start our final test. So regardless of what motor we're working with, the final test steps are all the same. This first step is a calibration procedure. This is when the Linea is tracking movement from the encoder, making sure that the movement that it sees is what is expected based on the dropdowns that we selected. And is essentially just a synchronization process between the Linea, the feedback device, and the run well drive. All right, so once that first step is complete, the Linea is reprogramming the drive to do an alignment check, called a commutation check, to make sure that the alignment of the encoder is good. Again, based on our drop downs here at the top. All right, so as you can see here in our run status window, the expected value at the U negative VW positive locking angle is 0 electrical degrees. And it is checking every possible locking angle as the run well rotates the shaft around. but it is only recording the one that it expects to find at U negative VW positive. So this is where it's important to make sure that you have your motor pole pairs selected up here correctly. Because if you select the wrong number of pole pairs, it's going to find the wrong electrical value as it goes through the different positions. With certain smart encoders, we can auto-populate the pole pairs for you, but in this case, you do want to make sure your pole pairs are correct. Make sure it's an 8-pole motor, not a 10-pole motor, etc. The good news is if you did make a mistake in the pole pairs, or even if the alignment's bad, if it doesn't find the expected value of 0 electrical degrees, at this point, the final test would stop and it would revert you back to the previous screen before we move on to analytics and start using our actual test minutes. Okay, so it looks like our alignment check is good. And what's happening now is the Linea is gathering the amperage feedback data from the run-well drive. And we are injecting the maximum amount of current into the different phase windings based on, how we programmed the drive in the previous step. So this kind of serves as a semi-load test or stress test on the phase windings, which will be included in the final report, which you'll see at the end. Obviously, this is not a replacement for your basic safety checks, your bench checks. Making sure that the phases are insulated from ground. The phases aren't shorted to each other, anything like that. But this will give you a pretty accurate determination of what condition your motor stator is in. All right, and now we are on to the first analytics portion of the test. This is when we're actually doing analytics on the encoder itself. And this is when having the closed loop system really comes in handy, because the drive can rotate the shaft of the motor and thus the encoder independently of your Linea X3 performing full resolution and complete diagnostics on the encoder, while taking into account that we have the encoder hooked up to an actual running motor that has, an electric current running through it. Also the magnetism from the rotor. It gives you a much more accurate idea and a much more accurate look of how that encoder is going to behave when it's in actual operation. So again, only one channel, so only 1 minute for the analytics before the pre-run time. The motor is now pre-running. And again, normally I would run this for at least 30 minutes, but this would be the time I would listen for bearing noise, which in this case, I can definitely tell that the PE, the front end bearing, needs to be replaced, judging by that grinding that I'm hearing. But bearing noise, brake noise, any kind of abnormal vibration. And again, if this is running for 30 minutes, it won't take you that long to check that. You just let it run. Go do your thing. We'll set something else up until the test completes. Or I'm sorry, until the free run completes and move on to the next part of the test. All right. So after the free run portion, this is our second calibration phase, basically just a repeat of the first calibration. Make sure we still have good communication with the encoder, resynchronizes, the motor speed to the count of the encoder, and is remeshing the linea, the run-well drive, and the encoder all together. All right, and then once again, the linea is now reprogramming the run-well drive to do a second commutation check. And it is important to do the commutation check before and after the free run time, because if something as far as the alignment or the installation of the encoder was loose or not quite right, and there we go. Sorry, I got distracted. And that only became apparent after the motor was running for 1,000 RPMs after half an hour or so. That's why we check the alignment before and after the free run time. So if like the coupler on the back of the rotor is loose, not tight as it should be, if maybe I didn't tighten down all the screws all the way and something drifted during that free run time, that's why we do the alignment check before and after, just to make sure before you send it out that the alignment is good. Yeah, it looks like it's still going to pass. If you're an experienced user of our equipment, you probably noticed by now that the found value, or the one that it cares about closest to the zero here, it will spend an extra half second on that lock-in position to record the found value. Just like that. All right, so it looks like we passed the alignment check again. So the final stage is to do one more analytics phase on the encoder channel. Except now, presumably, that encoder is kind of nice and hot, maybe even hot to the touch. It's under a certain amount of heat stress. And it is important to check those signals both when the encoder is cold and when it is hot. Because when you're talking about electronics and passive components, a lot of times if there's a problem with one of those passive components, like on the circuit board of the encoder, it may not present itself until it's under heat stress. And that minute is up. And our report pop-up has generated itself again, so we will go ahead and fill that out. All right, let's see what we got. All right, so again, here's the information we filled out, except now the module used is run well instead of analytics. And our overall encoder condition is still excellent, with no critical faults or out of bound occurrences, with the same kind of percentages we found during analytics testing, about 97.5. You can see here the summary also includes the channel summary. Again, there's only one channel, so we only have one to look at, but it also includes verification that your alignment is good. And then on the graphs page, there's our voltage average, any out of bounds or fault occurrences, our data points kind of right in the middle there where we want them to be. But in addition to up here, down here is where you have that stator check that we did before the first round of analytics. So you can see the U, V, and W phases, the wavelength and the amplitude for all three of them seem to be right about the same. They're all switching when they're supposed to. So that's a pretty good indication that the stator's in healthy condition as well. And then again, here are the data points collected for the overall test there. So again, especially for this one being a final test, I would save this as a PDF to send to my customer or my boss or whoever needed to see the final result. But this report is automatically saved, and you can go back and view it at any time through the AutoQ software using, the preferences there. So that's it. In this case, I would definitely go in there, rebuild the motor, and replace those bearings. But that is how you do analytics, alignment, and final testing on a Yaskawa Sigma encoder. Thanks for your time. As always, if you have any questions, you can email us at hello@octavaengineering.com. Or if you have a technical question, we are always available to help. Just shoot us an email at support@octavaengineering.com. Otherwise, I hope you found this helpful, and I thank you very much for your time.